Okay, everyone. So in this video, we're going to work on another method of approximation using a different rule called a trapezoidal rule. So how can we develop this rule? So let's go back to what we have. If we have this picture like the graph of x squared from 0 to 4, and from the previous lesson, we had approximated the value of the definite integral using what was called left, right, and midpoint approximations. So we created 4 equal subintervals, or as many as we would want, and we created equal subintervals, and we either chose the left endpoint, the right endpoint, or the middle. Well, there's another way to approximate the area under the curve bounded by the x-axis here, and that rule is called the trapezoidal rule. So what geometric figure do you think we would use in this approximation? Well, not rectangles, but trapezoids. So let me see if I can maybe make this picture a little better and just in general. So if we have something that looks like this, maybe blow up that x squared a little bit better. And then here it is, and get rid of that. And maybe this is it right here. So this time, I'm not going to create rectangles again. I'm going to create equal size rectangles, equal widths, trapezoids, I'm bad. So there's 2, and now 4. Okay, so like we see right here, this one has no height right here. So this right here would be my first trapezoid, where really you don't have a height right there. It really ends up being a triangle. But this here would be my second trapezoid now, right here. Remember, trapezoids are quadrilaterals where exactly one pair of sides are parallel, and those are called your bases. So if this is our first 0, x sub naught, and this is our set, we'll call it x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. Okay, just generally speaking. And the area of a trapezoid is 1/2 the height times the sum of the bases. And again, the bases are the parallel sides. And your height right here is perpendicular to the bases. So this is your height. So your height in each of these is equivalent to delta x. And delta x is the same for each of these subintervals. So it's a common factor thus. So this here, right here would be, well, I put x sub 0 into my function, I'd get y, and that's y sub 1, or y sub naught, which would just be 0 in this case. I put x sub 1 in, and I would get y sub 1. Put x sub 2 into the function, I get y sub 2. Put x sub 3 in, I get y sub 3. Put x sub 4 in, and get y sub 4. And then I'll begin finding the area of each trapezoid. So the area is 1/2 times the height, which is delta x, times the first y, y sub naught, plus y sub 1. The area of the second trapezoid is 1/2 times delta x, times y sub 1 plus y sub 2. The area of the third trapezoid is 1/2 times delta x. This is my third. So it's going to be y sub 2 plus y sub 3. And the area of the fourth would be 1/2 times delta x times y sub 3 plus y sub 4. So again, not much of a trapezoid here because the first height, the first base is 0 there. And here's my second trapezoid, my third trapezoid, and my fourth trapezoid. To get the total area, I'd simply add all of these up. And we can kind of see here that when we go to add all these up, the area would be equal to, well, 1/2 is a common factor in each of those. And delta x is the same for each. So I can factor that out. And then what I have here is I have one of the first y's, y sub naught. But notice that I have 2 y sub 1s, 2 y sub 2s, 2 y sub 3s, and 1 y sub 4. So I have 2 times y sub 1 plus 2 times y sub 2 plus 2 times y sub 3 plus y sub 4. And that's a general rule for a trapezoidal sum when we have the equal subintervals, because we factor out that delta x when delta x is common. If delta x is not the same for each subinterval, then it's recommended that we find the area of each trapezoid and just simply add them up. But this is just a general pattern of the trapezoidal rule when we have equal size subintervals. And it makes good sense because you only have one y of the ends, this y and this y here on, they're only one of each, because the y's in the middle are a common base to two trapezoids. Y sub 1 is a base to this trapezoid as well as the second trapezoid. Y sub 2 is a base to this trapezoid as well as this trapezoid. And y sub 3 is a base to this trapezoid here as well as this trapezoid. So that's why we have the y's being all doubled in the middle and only one y on the ends. But don't feel the need to memorize that because most often you just do the area of each trapezoid and add them up. So let's just do a little quick recall here. Here we got this function, and we're to this definite integral, and we're to approximate the value of the definite integral using these methods. And we're going to use equal subintervals. So delta x equals 5 minus 0 over 5, which is 1. And our x's will be 0, 1, 2, 3, 4, 5. Just count by ones. And we should have 5 subintervals. So the left rectangular approximation method is, well, delta x is 1. The left endpoint here is 0. So it's 0 squared minus 1 is negative 1. Plus 1 times the left endpoint here is 1. 1 squared is 1 minus 1 is 0. The next one is 2 squared is 4 minus 1 is 3. The next one is 3 squared is 9 minus 1 is 8 times 1. Plus 1 times 4 squared is 16 minus 1 is 15. I should have a total of 5. 1, 2, 3, 4, 5. And you could finish out the arithmetic. The right would be, well, delta x is the same, but now I'm going to take this as my right-hand endpoint. 1 squared is 1 minus 1 is 0. Plus 2 squared is 4 minus 1 is 3. Plus 3 squared is 9 minus 1 is 8. Plus 4 squared is 16 minus 1 is 15. And 1 times 5 squared is 25 minus 1 is 24. The midpoint, I won't simplify these just for the sake of time. It would be a half, 3 halves, 5 halves, 7 halves, and then 9 halves. So it'd be 1 times 1 half squared minus 1 plus 1 times 3 halves squared minus 1 plus 1 times 5 halves squared minus 1 plus 1 times 7 halves squared minus 1 plus 1 times 9 halves squared minus 1. And actually what you could do, because all these are just multiplied by 1, you could just do the arithmetic as 1/4 minus 1 plus 9/4 minus 1 plus 25/4 minus 1 plus 9/4 minus 1. Let me just make sure that's 49/4 minus 1. Because that's 1/4, 9/4, 25/4, 49/4, and then plus 81/4 minus 1. And you can group all your quarters together of like denominators and minus ones. Now the new one, the trapezoidal sum. Okay, so what we do now by the trapezoidal rule is I like to do the area of each trapezoid. So it would be 1/2 delta x is 1 times our first 0, which is f at 0, plus f at 1, plus 1/2 times 1 times f at 1, plus f at 2 plus 1/2 times 1 times f at 2 plus f at 3 plus 1/2 times 1 times f at 3 plus f at 4 plus 1/2 times 1 times f at 4 plus f at 5. And you can see from the pattern again, we're only going to have one y evaluated at 0, one y evaluated at 5, but we'll have two f at 1s, we'll have two f at 2s, two f at 3s, and two f at 4s. And then we're just going to substitute those in, and that's a 1 there. F at 0, 0 squared is 1 minus 1 is -1, and 1 squared minus 1 is 0. And f at 1, 1 squared is 1 minus 1 is 0. That y repeats. 2 squared is 4 minus 1 is 3. And then f at 2 squared is 4 minus 1 is 3. F at 3 squared is 9 minus 1 is 8. Then 3 squared again is 9 minus 1 is 8. F at 4 squared is 4 squared is 16 minus 1 is 15. And finally, the last one here would be, again, 15. F at 4 is 4 squared is 16 minus 1 is 15. And then 5 squared is 25 minus 1 is 24. And it should check out that, again, we only have one of the first y's, one of the last, but we will have 2 zeros, 2 3s, 2 8s, and 2 15s. The easiest way to go from there is to factor out the 1/2, factor out the 1, and then you go -1 plus the 3 plus the 11 plus the 23 plus the 39. And I should have a total of 1, 2, 3, 4, 5, and that looks good to me there. And you can finish out the basic arithmetic from there. The actual value is by calculator, where we would hit Math 9, and we'll take a look at that now. So we'll go Math 9. The lower limit is 0. The upper limit is 5 of x squared minus 1 x. And the actual value is 36 2/3. So 0 to 5 of x squared minus 1 dx is 36 2/3. Now, how does the trapezoidal rule compare to the actual? When the graph is concave up, trapezoidal rule, when the graph is concave up, think up and over. Up is greater. The trapezoidal rule is greater than the actual. If it's concave down, think down and under. The trapezoidal rule is less than the actual. For a midpoint, it's the very opposite. The midpoint would be, if it's concave up, the midpoint's less than the actual. And when it's concave down, the midpoint's just the reverse. It's greater than the actual. Okay. So naturally, up and over, trapezoidal rule uses concavity as well as midpoint. The midpoint may go against your intuition, but if you look at the graph of this x squared function, if you just look at the graph of x squared and you partition it into 4 equal subintervals and you create trapezoids, you could see that you would have more area than, it's an over approximation to the actual value of the definite integral. So you could see that when the graph is concave up, the trapezoidal rule will be greater than the actual value, up and over. Now, how do we know that? Well, the function itself is x squared minus 1. Its derivative is 2x, which is greater than 0, which means f is increasing on those x's from 0 to 5. So if it's increasing on that interval, then a left Riemann sum is less than the actual and the right is greater because those are your two extremes. The second derivative is 2x. I'm sorry, I'm bad, just 2, which is always greater than 0, regardless of what x is. So this graph is always concave up. And in particular, it's concave up on the interval from 2 to 5. So therefore, if it's concave up, then the midpoint will be less than the actual, but the trapezoidal will be greater than the actual because it's concave up. Okay, so let's see what other problems we have here. I'm not sure if I like those as much. I'd rather just hop, skip, and a jump to, well, let's do one more here. But I may tweak this function here to be something. Yeah, I guess I'll do this one here. We know the left and the right. I'm not going to do those again for the sake of time. I'm just going to do the trapezoidal rule and just perhaps set that up. So once again, your first step is to get delta x. And delta x here is 4 minus 2 minus 0 over 4, which is a half. So my x's are 0 plus a half plus 1 plus 3 halves plus 2. Notice that the trapezoidal rule uses all of the x's. So the trapezoidal rule, using this function, e to the negative x, would be, maybe I'll come over here, 1/2 delta x here is worth a half. The first x is e to the 0, and e to the negative 0 is just 0, plus e to the negative 1/2, plus 1/2 times delta x, which is a half. Now I'm on this interval. So it's e to the negative 1/2 plus e to the negative first. Now I am on this interval, plus 1/2 times 1/2 times e to the negative first plus e to the negative 3 halves, plus 1/2 times 1/2 times e, now I'm on this interval, e to the negative 3 halves plus e to the negative second. And as once again, we suspected, we will have only one of these appear, but we should have 2 of these and 2 of these. So if I wanted to do some cleaning up, I really could factor out from each of these a 1/2 and another 1/2, which would now be a 1/4. And that'd be e to the 0 plus, I could obviously see by like terms, I'm going to have, which we know here's 1, 2e to the negative 1/2 plus 2e to the negative first plus 2e to the negative 3 halves plus e to the negative second. And so just to double check there, I've got 1, 2, 3, 4, 5, 6, 7, 8. And that looks good to me there. So it'd be e to the 0 is 1. I doubled all of these. All of these had gotten doubled. All of these y's got doubled because with the trapezoids, these are bases between two trapezoids. This is a base between the first and the second. This is a base between the second and the third. And this is a common base between the third and the fourth. And that's why that makes sense. It gets doubled. And then, of course, right here, this could just become a 1/4. Okay. Next up is using a free response question. Okay, so like this is important right here. So in this question, we're presented with motion. And it is the velocity of a particle moving along the coordinate axis, and its positions given by x. X is measured in meters, velocity is meters per second, and time is in seconds, and selected values are given. We're to approximate the value of this definite integral using the 5 subintervals indicated in the table. Notice they didn't say equal. So therefore, we're going to have, this is one interval. This is my second. This is my third. This is my fourth. And this is my fifth. So the left, rectangular approximation. is the difference in the x's, which is 8, times, this is my y value. It's my y value, oh, at my left. It's not 8, it's 0. Boy, oh boy. So in this interval, 0 is my left. The velocity when t equals 0 is 3 at that left endpoint. Now in my second interval, 20 minus 8 is 12. Delta x is always positive. Times the left endpoint. So v at 8 is 5. Between 25 minus 20 is 5. And the velocity at 20, the left endpoint, is negative 10. Between 25 and 32, the difference is 7. And the velocity at 25 is negative 8. And between 32 and 40, the difference is 8. And the y value is negative 4. The right rectangular approximation method. Well, the delta x's won't change. So why do I have that as 0? That should be 8. So that's 8. So it's 8 minus 0, and then 20 minus 8, and then 25 minus 20, and then 32 minus 25, and 40 minus 32 is 8. And the left end points would be 3, 5, negative 10, negative 8, negative 4. As I've said, always one of the values gets left out. Since it's the left end point, the far right will get left out. Now, when it's the right-hand endpoint, the far left will get left out. So the delta x here in the first interval is now corrected to be 8. The right endpoint is 5. Again, between here and here, the difference is 12. But the right-hand endpoint, when t is 20, the velocity is negative 10. And between these two, the difference is 5. And the right-hand endpoint is negative 8. Between these two, the difference is 7. The velocity is negative 4. And between these two, it's 8. And the right-hand endpoint is 7. So again, the far left would be left out, and that's a 3. Now the trapezoidal rule. Okay, so we do them by hand. So it's 1/2. So remember the area of a trapezoid. A equals 1/2 times delta x times the sum of your bases, which are your y's. That's the height of the base at those x's. This is always the difference in your x's. So then the first one again is 8. Maybe I'm losing sight of that there. So that's 8. And then it's 3 plus 5. This uses all of the y's. Plus 1/2 times 12 times 5 plus a negative 10, which is just minus 10, plus 1/2 times 5 times negative 10 plus a negative 8, plus 1/2 times 7 times negative 8 plus negative 4, plus 1/2 times 8 plus negative 4 times 7. So again, you would see here that you have the unequal size subintervals, so you can't factor out the delta x this time because it's not common for each trapezoid. The size of each subinterval is not the same. I just realized I just did the whole thing from 0 to 40, but it said only 20 to 40. So if we wanted only 20 to 40, then that means we would go from here to here. Erase. Okay, so then draw 20 to 40. So I stand corrected. Not perfect, I am. Look always at the limits of integration. So then that's okay. So the 3 intervals would be from 20 to 25, 25 to 32, and 32 to 40. So that rate there will be equal to 1/2, and 25 minus 20 is 5. and negative 10 plus a negative 8, plus 1/2 times 7 times negative 4 plus negative 8, plus 1/2. Again, these are your delta x's. 40 minus 32 is 8, plus negative 4 plus 7. And as you would expect, we'd only see one negative 10, one 7, but we would see here, yeah, just put it in a different order. We'd see two negative 8s, and we would see two negative 4s. Okay, just as a highlight there. And again, the only way to clean that up is you could factor out the 1/2, but you'd have to really just add these right here and then multiply. So you would have to do here, to do that, you would do 1/2 times 5 times negative 18, plus 1/2 times 7 times negative 12, plus 1/2 times 8 times 3. And you can clean that up from there by the order of operations. This would be here, half of negative 18 is negative 9 times 5 is negative 45. Half of 12 is negative 6 there, times that is negative 42. And then that would be then, of course, 12. Okay. Now, what if we came along and we wanted the value of this definite integral, where it's the absolute value of v at t dt? Well, nothing much would change, except you would take the absolute value of all your velocities, and you'd now make them all positive. So then now, if we do that, what will be this answer in part C, using a trapezoidal sum, where we take the absolute value of all our velocities? So this would be then 1/2 again. And we're only going to 20 to 40 this time. So the difference here is 5 times positive 10 plus positive 8, plus 1/2 times the difference in these x's is 7, times 8 plus 4, if I can see it right, plus 1/2 times 8 times 4 plus 7. So this would produce then, well, 18 divided by 2 is 9 times 5 is 45. 12 divided by 2 is 6 times 7 is 42. And that's going to be a little different now. That's going to be half of this is 4 times 11, I believe, which is what? 44. Now, what is the interpretation of this now? What is, now we were to interpret our answer. So remember, interpreting definite integrals, we use what's called as the nut strategy: noun, units, and time. So here, if I copy the integrand over again, this is the absolute value of velocity. Well, the units are still meters per second, and the change in time is still in seconds, so I still end up with meters. So the units belonging to my answer are meters. And I know the interval of time, it's from 20 to 40. But the noun describing my answer is, it's not the change in position. It's not the net distance. Remember my story that when I made my velocities from 0 to 4, when I made the negative 65 now a positive, when I wanted the total distance traveled, any area that was negative, I made positive. Thus, this represents the total distance traveled in meters from t equals 20 to t equals 40 minutes. Wait. Made this up on a fly. Okay, so it's the total distance traveled. Okay, if the back here, when I took into account the velocities being negative and somewhere positive, then that would represent the change in position from when t had equaled, say, in this case, 20 to t equals 40. So this would represent the change in position in meters from t equals 20 to t equals 40. So again, I can't emphasize it enough that when this rate here, the absolute value is on the function in the integrand, which was, where was it at? Right here. It takes those y's that were negative, which is below the x-axis, and flips them over to now becoming positive y's, positive velocities, and now all of my area has turned to be positive, which represents the total distance traveled, rather than up in part C was the change in position, the change in position in meters from t equals 20 to t equals 40. And this was the total distance traveled. So again, the bottom line is we got the trapezoidal rule, and it's nothing more than find delta x, get each of your x's, and the area of a trapezoid is you do it one at a time. A equals 1/2 times delta x times your first y plus your second y, which comes from putting in your first x, your second x. So the trapezoidal rule uses all of the x's, all of the y's, but as a pattern, you will see that all the y's in the middle will get doubled, and on the ends, you'll have one of each. You'll have one y on the end, the beginning, and one y at the end there. Okay, but again, you don't really need to memorize that at all if you just simply find the area of each trapezoid and add them up. But again, the delta x is, your b minus a over n, or it is, and that's when it's equal size, or it is just your difference in your x's. Here, the delta x was the same for each. But in this example, the delta x was not the same. So back here, the delta x was not the same. Here in this case, it was 5. As you can see right here, we went from here to here. This is 5, delta x is 5, delta x is 7, delta x is 8 there. And then this is, when you do 1/2 times 5 times the first y plus this y, that's your first trapezoid. And then between here to here, it's 1/2 times 7 times 8 plus 4 plus 1/2 times 8 times 4 plus 7. Just can't reinforce it enough. Okay, well, I hope that helps you with the trapezoidal rule and approximating a definite integral.